In the previous video, we took a look at an example where a function passes not just a single variable, but a row vector into a function, and then the function returns several row vectors, and then we're able to print them out in a fairly organized fashion using a for loop. So a pretty good example of using both of the concepts that we've learned. Let's take a look at one last smaller example, and then we'll take a look at a cumulative example where we kind of rope a lot of things together. And so this is a pretty common sort of parametric relationship, is that we have a trajectory and we're given an initial velocity in meters per second and an angle in radians. And the program is going to go through and ask the user for a time span, and then it's going to process the velocity, the initial angle, the initial velocity, the initial angle, and the time, and it's going to produce a path, right? And it's going to restore the x and y variables as row vectors, and it's going to pass it back, and it's going to produce a scatter plot. So essentially, the function is just going to do this right here. The row vector or the time vector is going to be in increments of 0.25 seconds, and these are just some test parameters that we can use to determine if the function or if it works or not. All right, first thing we need to do, we need to get a velocity and an angle in radians and a time. So let's do that easy stuff first. So first things first, we're going to say, I'm just going to call it theta, or actually we could just call it A for the angle. And we're going to say input, and we're going to say enter an initial angle. And we have that. And then let's call V the initial velocity, and it should be enter an initial angle. We're going to input an initial velocity. And then we're going to enter a time. Now I'm going to call that time, and that's going to be equal to input. Let's say enter the number of seconds the object travels. All right. And if we want to be really specific, we should enter the initial angle in radians. Right. And then finally, we're going to input the initial velocity in meters per second. All right, so that should take care of all that. Now, actually, I think, let me make sure I've read this correctly. It's going to, so it says to enter the initial angle in degrees. All right, so we'll convert it when we get down there, no big deal. Okay. Now our time, let's create a vector t, a row vector, and time t is going to be 0. Remember, it said 0.25 seconds, and then we had up to time. All right, so that's basically going to be a row vector of time increment in 0.25 seconds. All right. And now at this point, I think we can actually build the function. So function, and the function is going to return the x coordinates and the y coordinates. And that's going to be equal, I think we wanted to call it trajectory. Not trajectory, trajectory. And we're going to pass in several variables. So we're going to pass in an angle, and we're going to pass in the initial velocity, and we're going to pass in the time t. Right? Now remember, t is a row vector. All right, so when we pass this in, a and v are both constants, but t is a vector. So that means we have to make sure we use vector multiplication instead of scalar multiplication. All right. When we compute the formulas, all right, so remember that x is equal, if we go back, we know that x is equal to v sub naught cos theta t, but theta needs to be in radians. So let's do this. Let's say a, it's going to be entered in degrees. So a is going to be equal to, we're going to say a times pi over 180. All right, so that's how we convert that angle really quickly. So x is going to be equal to, and we have our formula, v sub naught cos theta t. All right, so that's easy. That's going to be v times the cosine of the angle dot times vector t. Right, so now we have a row vector x. Now we want a row vector of y. And if you look at our formula, it's almost the same thing, except we're going to subtract out this acceleration due to gravity. All right, so this is going to be 0.5 gravity times t squared. All right, so that's going to be our y times v sub naught sine theta t. So we could basically copy. We need to define what gravity is. And gravity is 9.81 meters per second. So when we do this, we're going to have a gravity constant, which is 9.81. And y is going to be equal to v times sine of a dot times t minus the gravity, or 1/2 of the gravity, dot times t dot square. All right, so now we have a y, and that's going to end our function. So this does all the conversions for us to be able to find what our x and y coordinates are going to be. Now up here, we're just going to plot it. All right, so x and y. So now we're going to use the function is going to be equal to trajectory. And we're going to pass in the angle A, the initial velocity, and then also that row vector t. Now we're going to plot x and y. And we're going to use it as a scatter plot. So we're just going to use this as our marker. We could use that, might as well. And that should be it. So let's give it a go and see what happens. So our initial angle, remember we said was 45. The initial velocity, let me check what that was, is 50 meters per second, and the time is 8. So let's try 50, and let's try 8 seconds. And it's thinking. There we go. All right, and so we get this parabolic path, which we expected. It's concave down. And it looks like right about here at around 250, it hits the ground. And then after that, these are all non sort of sensical answers because it goes through the ground. It might be cool to put the graph or the grid on, so that way we can see a little bit more about this. So it was 45 and then 50 and then 8 seconds. All right, so it looks like right here, when x becomes about 230 or 235 meters, it looks like it hits the ground. And it looks like the highest point is somewhere around 65, maybe 63 or something like that. So now, of course, we could take the derivative and be able to find that, or even just use the vertex formula. All right, so it looks like 63, just kind of tracing over this. So maybe 64 or something like that. So pretty cool that we could do that. And the path helps us to be able to find what those values are for the travel. If we really wanted to, we could use an if statement and try to figure out what the highest point is, at least in this increment of 0.25. So we could just replace it. So if the value of t sub I is greater than the high, then you replace the high. But regardless, we've done what we've been asked to do for this. All right. So we're going to do one more example. And this is going to kind of take everything that we've seen so far and kind of put it together in one cumulative example. So we'll do that in our next video.